Hi everyone, this is Greg Ilg with Renaissance Electronics America, and today I'll be demonstrating the FIT configurator for the RX family of MCUs. FIT, which stands for Firmware Integration Technology, is a coding standard or set of rules which ensures interoperability across different RX MCUs. I am beginning with E2 Studio already open and in an empty workspace. E2 Studio is our Eclipse-based IDE. To create a project, I go to File, New, C Project. And today I'll be working with an RX-113. So I'm going to name my project RX-113 underbar FC for FIT configurator. And I'll be using the Renaissance tool suite, so I'll select RxC tool chain and click Next. For debug hardware, I have an E1 emulator. Now your RSK may have come with an E1 or an E2 Lite. Just select whichever emulator you have available. For the target device, I am interested in the 100-pin 8AX FP. This is the MCU present on the RX-113 RSK board. I will select that, then click Next. On this page, I want to select both the radio button and the checkbox for FIT. Then I want to click on Download FIT modules if I have not done this previously. This will download all the drivers from the web. Please pause the video if you need to do this now. Once you have done this, simply click on Finish. A summary box will appear and you can just click OK. Now when you expand the project, you will see that there is a single source file, which is basically your main.c file. In this file, there are a few lines of C++ which have been if-def'd out. Today we are just going to be programming in standard C, so I'm going to remove these lines from the file. Now that I have done that, I'm going to open up the FIT configurator. To do that, I go to Renaissance Views, E2 Solution Toolkit, FIT configurator. I will select the project, and here I will see a list of all the modules that have been downloaded. And what I am looking for is the Serial Communications Interface, or the SCI driver. And here it is right here. I will select that, then click Add Module. And I will see that that module, along with all the modules it is dependent upon, is added as well. In this case, the board support package and the BIQ library. When I select the SCI module, in the Pin Settings tab, I will see all the pins associated with this driver. For the RSK, I am interested in SCI Channel 1, and for transmit, I am interested in Port 1, Pin 6. Now I am ready to generate code, so I will click on the Generate Code button. Another summary box appears. I just click OK. Now the first thing I want to do is add the include files for each of these modules. For the BSP, I want to add platform.h. Now the BIQ module will not be called directly by my application, so I will not need to add that include file. For pin config, I want to add pinset.h. And finally, for the SCI driver, I want to include if.h, which stands for the user interface file. Next, I want to look at the configuration files. Now these files do not contain values that go into registers for the driver, but rather refers to overall configuration for the driver itself. For example, in BSP, here I can set up my stack size or configure which clock I want to run off of. So if I search for clock, here I can see that by default the clock source is set to 4, which corresponds to the PLL circuit. If I wanted to run off the HOCO, the high-speed oscillator, I would change this value to 1. As another example, I'll go to the SCI config file. Here I will see a table showing all of the MCUs supported by this driver, as well as all of the channels available on each MCU. An asterisk by a channel indicates that that channel is available as a COM port on that RSK. To include source code for a channel, I simply set the value to 1 next to that channel. Now when I say this, I'm not referring to actually including an entire driver specific to that channel, but rather just including a little bit of source code to add some pointers to the set of registers specific to that channel. Now that I have my high-level configuration done, I'm going to go back to my main program and add initialization code. I'll start with the pins. I'll open up pinset.h and see that the function pinset SCI1 has been created for me to initialize my transmit pin. I will copy that and paste that into my main function. And then I Control S to save it. By holding down the Control key and clicking on the function name, I should go directly to that function. This time, though, we just went to the prototype for that function. To get back to where I was, I will press the Alt key and the left arrow, and I'll return to my previous position. What I want to do now is right-click on the project name, go down to Index, and click Rebuild. Now this time, when I press the Control key and hover over the function name and click on it, I do indeed go to that function, and I can see how the transmit pin has been initialized. To return back to main, I'll hold down the Alt key and press left arrow. Now that I have initialized the pins, I want to initialize the SCI driver itself. For that, I will go to the user interface file. Now the majority of this file contains equates that are passed to the API functions, and these API functions appear at the end of the file. To initialize the driver, I want to use the open function. So I will copy that prototype and paste it into main. The first thing I want to do is create a return variable. And I will just call it error. And I'm going to make it a global variable. It could just as well be a local variable. Next, I want to start adding elements to pass into this function. I'll begin with the channel number. Now, as a general rule, you should go to the interface file and see all the equates that have been defined for the API. But most of the drivers also have what we call the type ahead feature. And to do that, you just type the module name, under bar, the first few characters of the variable, Control space, and you'll see the options available. In this case, I'm interested in channel 1. For my next argument, I need to enter mode. So I'll type in the module name, underbar, first few characters, Control space, and I'm interested in running in asynchronous mode, which is basically a UART mode. Our next argument is a pointer to a configuration structure. So for that, I'm going to first have to create a variable of the configuration type. I'm going to call that config. And then I'll put an ampersand before the variable because I have to pass a pointer to it. The next argument is a pointer to a callback function. Now, callback functions are called every time a byte is transmitted or received by the driver. This is used in unusual circumstances. For example, when you have a particular protocol where you have to look for escape characters. But in today's example, all we are going to do is send out a simple message. So I'm just going to pass in a null pointer instead of actually creating a callback function. Finally, we need a pointer to a variable of the handle type. So I will copy its type, create a variable called handle, and then pass a pointer to it to the function. Now I have completed the call to the open function. I still have to initialize the configuration structure. For that, I type in the variable name, dot, and here I'll see the options available to me. And I'm interested in the asynchronous configuration, or the UART mode. Hit type again, and I'll see all the options available in this mode, starting with baud rate. I'll set that to 9600. Next, I will set the clock source. So I'll start with the module name, underbar, first few characters of the structure element, control space, and I will choose to run off of the internal clock. We just repeat this process for every element of the structure. Next is data size. I'm going to set that equal to module name, underbar, first few characters, control space, and run in 8 data bits. Now for interrupt priority, I can see there are really no matches provided. So that indicates to me it is looking for a number directly, just as I did for baud rate. Interrupt priorities range from 0 to 15. 0 means interrupts disabled, and 15 is the highest priority interrupt possible. I'm just going to arbitrarily choose interrupt priority 3. And then I'm going to continue on initializing the remaining elements of the structure. Next would be parity enable. Module name, underbar first few characters, control space, and I'm going to turn the parity checking off. And since I have parity enable off, I'm not going to enter any parity type and go directly to stop bits. I'm just going to use one stop bit. Now I've completed everything I need to do to make an open call and initialize the SCI driver. Next, I want to send a simple message. So I'll return to the interface file and copy the prototype for send. Now the first argument here is handle. Handle is initialized by the open call and is passed in as a unique ID to the remaining API functions for this driver. The next argument is a pointer to the source buffer of whatever it is we want to transmit. Rather than create an actual buffer, I will just simply hardcode in a simple message like hello world. And finally, I have to enter the length of the message, which in this case is 11 bytes. Always remember hello world is 11 bytes because the double L reminds me of the number 11. And that's really all we need to do for this program. I will just add an infinite while loop to spin after we send out this message. I will hit Control S to save the file, then go over to the project, right-click, and click on Build Project. I could just as well go to the hammer icon to build the project. Once the project has completed building, we are ready to download. But before we do this, we need to connect the RSK board to the laptop. To do this, we need to make 2 connections, one for the emulator and the other for the USB serial port. For this, we want to use the USB connector to the right of the power jack on the board and connect that to the laptop. Please pause the video now to make these connections. Once you have made the connections, you can download your program. To do that, you right-click on the project name, go down to Debug As, and select Hardware Debugging. Alternatively, you could have clicked on the bug icon to debug your application. When you are prompted to go to the debug perspective, select Yes. This perspective opens up additional windows that allow you to inspect variables, look at the callback, and have other additional features provided to you. Now, before we actually run this, we have to set up a terminal program on our laptop to receive a message. To do that, I'm going to use TerraTerm. I'll open it up, select Serial Mode, And I want to select the COM port that says RSK USB serial port. Alternatively, you may have Seger CDC COM port, which will also work. If you don't have either one of these available, you will need to download a driver from the web. To do this, go to the company website, www.renesas.com. In the search box, type RSK USB serial driver. Once the search is complete, scroll down until you find this entry. Click on this to download the program and then install it. Please pause the program if you need to do this now. After you have installed the driver, you'll need to reopen TerraTerm, select this COM port, and click OK. You can go to the Setup menu and click on Serial Port to see how its driver has been configured. And you will see it matches our defaults, 9600 baud, 8 bits, no parity, 1 stop bit. So I'll just click OK. I'll now return to E2 Studio. To run our program, I click on the play icon, and this will run until we reach main. And then I'll click on it again for it to run the rest of the program. When I open up the TerraTerm window, you can see that we have successfully sent the message Hello World. So now in about 15 minutes, we have managed to create a project, added drivers, configured the drivers, wrote a simple application, built the application, downloaded it, ran it, and verified that it worked properly. Again, all in about 15 minutes. For more information, please go to our website, www.renesas.com. Thank you.